Hello, this is Anand Paul and welcome back to civildigital.com. In this session, we will learn how to perform time history analysis of structures under seismic accelerations in Staad Pro. In time history analysis, we apply data over increment of time steps as a function of acceleration, force, moment, or displacement. The result that we will get is the response of the structure over time during and after the application of load. The time history response of a structure is simply the response evaluated as a function of time, including the inertial effects. Just like response spectrum analysis, the time history analysis has got two stages, where in the first stage we will define the time history function definition, and in the second step we will apply the defined definition to our model. So in this video we will perform the time history analysis on the structure that I have already created. It's basically a 3D concrete structure. The modeling and the assigning part is complete. So let me open the Staad file of the structure. So this is the structure that we are going to analyze. The first step to perform the time history analysis is to define the cutoff mode shape. So to assign the cutoff mode shape command, go to commands in miscellaneous. We'll define a cutoff mode shape of 25 and click OK. So as I explained earlier, there are two basic stages in performing the time history analysis in Staad Pro. The first stage is the time history definition. To define a time history definition, go to General, in Loads and Definition tab. In definition, select the time history definitions and hit add. Now the time history definition window will pop up. We will provide a type value. It is nothing but the title or the name of our definition, but it should be a numerical value. Let it be 1. The loading type that we are going to use is an acceleration time loading, for which we have to enter the acceleration versus time values. In this example, we will use an external input file that I have already saved on my desktop as a text file. So I'll open it and show you how it looks like. So these are time and acceleration pairs. On the left side it is the time, and on the right side you can see the acceleration value. We have this time versus acceleration input for around 31 seconds, and to use this for the loading, it is necessary that we should save this input file in the same folder where we have saved the Staad file. So I'll copy this and paste it in this time history analysis folder. Now I will specify the external file name as input.txt for loading. If you are using a normalized input file, or you want to bring down the units or scale down it to your present input units, you might have to specify a scale factor, but Staad does not provide a direct method to provide the scale. You might have to edit the Staad input file in the editor to provide a scale. I'll show you how to do it. First, let's complete the definition part. I'll hit add to accept the definition. And after adding the time history definition, we will have to set certain parameters. The first parameter that we have to define is the time step. A time step is nothing but the time increments or the delta t value used for the analysis. The time step or the output time step size should be small enough to provide a sufficient resolution for the analysis. The lesser the time step, the more will be the analysis resolution. The required resolution depends on the characteristics of applied loading and the structural properties such as the natural periods. We will use the default time step value, and after that we have to input the damping value. We will use a damping value of 0.05, and if you don't know how to use the cdamp and mdamp option, I'll explain it to you in the next video. And after that we'll have to specify the arrival time. Arrival time is the time at which the load assignment begins. It can be positive, negative, or 0. For negative arrival time, the portion of input which occurs before the time 0 is ignored. For example, an arrival time of -5 seconds will neglect the first 5 seconds of the input function. I will input values 1, 2, and 3 as arrival time. The arrival time option comes into use when you know the actual time when the loading starts, like in mechanical loading or machine loadings. we know the actual time at which the loading starts. The purpose of inputting more than one arrival time is that we can select the arrival time which you want to consider in the analysis or the specific load case. I will explain it when I assign this load to the structure. So the definition part is complete. Hit add to accept the definition. As I said earlier, if your input is normalized or you want to specify a scale, you will have to open the Staad editor. Next to acceleration, you will have to specify a command scale after leaving a space and the scale value. If you want to save the changes, hit save and close the editor. So if I was using English scale, I would have specified a scale of 32.2 to convert it to English units. So the first stage of time history analysis is complete. In the next stage, we will define load cases to apply the defined loads and other static loads acting on our structure. We will define 3 basic load cases and 2 combinations to perform the analysis. The first load case will consist of the self weight of the structure, and in second load case we will apply the flow loads that are acting on our structure, and finally in third load case we will assign the defined ground motion to the structure. So first of all, let us define the static loading. I'll select the dead load case, and next to load case I'll type in a title dead and hit add. In the dead load case, we will consider only the self weight of the structure with a factor of -1 in y direction. Hit add. We will assign it to the whole structure. We will add another load case with static flow load. Let the type again be dead. Hit add. To add a load item, select the load case and hit add. We will assign a flow load in y range with a value of -5 kN per meter square in global y direction with a y range of 0 to let it be 20. Again, the x range is 0 to 20 and z range is 0 to 20, and we will hit add. If we select the load item, we can see that the Staad has automatically detected the flow levels and assigned the flow load that we have assigned to the structure. And finally, the third load case, which is the dynamic load case, I'll select the type as seismic and hit add to add load items. Again, in the dynamic load case, we will add self weight of the structure in global x, y and z directions, because we assume that the self weight of the structure is acting or is seismically active in x, y and z directions for the analysis purpose. Again, the flow load of 5 kN per meter square in global x, y and z directions with the same x, y, z ranges. Finally, we'll assign the time history load. To apply the time history load, click on the time history option, and in time history select the ground motion. We will apply the ground motion in global x direction. Use the drop down menu to select the direction, and we will specify the arrival time. We'll specify the arrival time as 2. Now you can see that all the values that we had provided in our definition, that is 1, 2, 3, are showing here. Or if you want to specify one arrival time in one load case and some other arrival time in next load case, you can make use of this option, and in type select acceleration. Let us provide an amplitude factor of 1.5. It is nothing but a multiplying factor. Hit add to accept the definition. We'll assign the self weight to the whole structure. If you take a look at the ground motion command, you can see that it has got 2 values, actually 3 values, that is 1, 2 and 1.5. The first value refers to the first time history definition, and next value 2 refers to the second value in our arrival time list, which is 2 seconds. And the third value is the scale factor, and x denotes that the ground motion is applied in the global x direction. Now we have to add load combinations to obtain the envelope. Let the first load combination be static dead plus flow load plus the dynamic in x direction or in positive direction, and the second one with a dynamic load case factor of -1, which will apply the dynamic load negative direction, and hit add. You might have noticed that in the dynamic load cases we always use a positive values. That is basically because we are only bothered about the magnitude of the load which are used to calculate the mass of the structure. So it is always good to use the positive values while assigning the dynamic load cases, just like we did in the static or the response spectrum analysis. So now the loading part of the analysis is complete. Now let's move forward and assign the perform analysis command, and now switch to post print tab. We will add the command to print the analysis results and hit close. Now the structure is ready for analysis. We will hit the run analysis command, and the analysis is complete with 0 errors and 1 warning. Let us check out the output file. Select the output file option and hit done. So this is the output file. If you have already watched the response spectrum analysis, we know how to deal with this warning and what has caused this warning in the analysis. We will check out the results. In the eigen solution, the Staad has calculated the mode shapes from 1 to 25 and the corresponding frequencies and periods. Scrolling down, the Staad has calculated additional mode shapes from 26 to 42 for our reference. Just below it we can see the participation factors, and we have achieved a participation of 99.99% in x direction and 100% in z direction, and Staad confirms that a damping value of 0.05 has been used for mode shapes from 1 to 25. Just below that we can see the time step used by the Staad in time history analysis is 0.00139 seconds, and 25 mode shapes has been considered for their contribution. Again, the time duration of the time history analysis is 34.16 seconds, which makes the number of time steps in the solution process as 2400/595, and the base shear in x, y and z directions are printed, and the times at which the maximum base shear has occurred has been printed just below the base shear value. If you scroll down, the joint displacement value for each and every joints for the load cases 1, 2, 3, 4 and 5 are printed. You can scroll down to view the joint displacement values. Below the joint displacement value you can find the support reaction values for the load cases 1 to 5 for each and every supports, followed by member end forces of the elements of the structure. Now let us switch to the post-processing mode, where we can graphically view the analysis results. We will select the combination load cases to study the analysis results. Switch to Dynamics tab, where you can see the mode shapes, the time displacement results, time velocity results and time acceleration results. You can scroll down to view the various mode shapes from 1 to 25. To view the time history analysis results, first of all we'll check out the time acceleration results, and Staad pop-ups a window asking if you want to create a node group. We will hit yes. The purpose of creating a node group is that we can get the average of the nodes. It might be acceleration, displacement or velocity of the node group that we are creating. We will create a node group of the roof flow. Let the name of the node group be roof, and hit OK to select the nodes. I'll select the roof nodes and hit associate. Now it will associate the roof nodes to the group name called roof, and on the right side you can see the acceleration in x, y and z direction for a loading time of 0 to 34 seconds which was the last input of our loading input file. If you want to check out the acceleration of individual nodes, you can select the nodes and the software will automatically update the acceleration values. Now let us check out the displacement results of the analysis. If you want to check the displacement of a node in the roof level, select the node. You can see that the maximum displacement in X direction is 6 mm and the corresponding Y and Z directions has been shown, and the maximum displacement in the positive direction has occurred at a time of 4.69 seconds. On the node just below the roof, the maximum displacement is 4, and it is obvious that the node just below it will be having much lesser displacement. If you want to see the combined or the average displacement of the roof nodes, you can select the roof node group, and the average displacement of the roof nodes is 6.34 mm. Leaving the displacement diagram on, the Staad provides us time slider, which can be used to slide through the analysis time and view the corresponding displacements. Let us keep a time as 4.7 seconds where we obtain the maximum displacement in the analysis. We'll reduce the displacement diagram scale to a value of 0.4 and hit OK. Now we can scroll up and down through the time slider and view the corresponding displacements from 0 to 34 seconds. You can see that the Staad automatically updates the displacement diagram while we slide through the slider in time. With this, let me conclude the video. In the next video, we will learn how to perform time history analysis using forcing functions like sine functions. I hope this was useful. For more videos and updates, subscribe to the channel Online Civil Digital, and thank you for watching.